All right, let's get started. Uh, Last time we stopped here, we talked about median and also the mean. What's the difference between these parameters? Okay. And we also get some example to calculate the median and also mean. Okay. Let's continue for today. Quartiles. Okay. So quartile divide the data as nearly as possible into 4 quarters. Okay, so median divide the data into the top and bottom half. Okay, so the idea of quarters and quartiles and median are pretty similar. Okay, the first quartile is the median of the lower half of the data. Okay, and here is how to find the first quartile. So calculate 0.25 times n plus 1. Okay, for median is 0.5 times n plus 1. And remaining will be the same. Okay, so if this is integer, then the sample value in that position is the first quartile. Otherwise, we take the average on either side of this value. Okay, so that's the first quartile. The third quartile is the median of the upper half of the data. Okay, so similarly, to find the third quartile, we calculate 0.75 times n plus 1. Again, if it's integer, then sample value in that position is the third quartile. If not, we take the average on either side of this value. Okay, and the median is equivalent to 0.5 times n plus 1. So median is actually the second quartile. Then let's look at percentile. Okay, similar to quartile, percentile just divide the data into percentage. So first of all, the p percentile of the sample for number p between 0 and 100. So we divide the sample so that nearly as possible p% of the sample value are less than the p's percentile. Okay, and 100 minus p% are greater. Okay, similar to what we calculated for quartile. Okay, so first of all, we order the sample size is n, from the smallest to the largest. Okay, and we calculate the quantity p over 100. For example, 11th percentile, so 11 divided by 100 times n plus 1. Okay, and here n is the sample size. Again, if this number is integer, then the sample value in that position is the p's percentile. Otherwise, we take the average of the two samples on either side. Okay, so same idea. All right, and you probably already guessed it. The first quartile is the 25th percentile. The median is 50th percentile, and the third quartile is the 75th percentile. Okay, so the idea is simple. The calculation is also very similar. Okay, let's have a look of sample calculation. Okay, right here we have data of 5 samples, 2, 3, 5, 6, and 7 is already arranged from the smallest to the largest. Okay, so what is the mean of this data? Okay, so let's just do this simple calculation together. What is the median, what is first quartile, and what is third quartile? Okay, let me share my iPad with you. Okay, we are here. So the means is very simple, right? For the mean, we just add everything together and divide by the sample size. Okay, so that's 2 plus 3 plus 5 plus 6 plus 7 divided by sample size, which is 5. So that is the mean value. Okay, the median, we calculate n plus 1 divided by 2. Okay, so n here is the sample size. So n is 5, so n plus 1 divided by 2 is 3. So that's integer. So that means the median will be the third sample. Don't forget to arrange the sample item from the small list to the largest first. Okay, so the third one is 5.
Looks like you're showing, Professor.
Oh, I'm sorry. Oh. Oh. So you cannot see my... let me do it again. Sorry. How about now? Can you see the...
Yep. Yes.
Okay, great. Thank you. Yeah, sometimes the connection between my laptop and the iPad is not working. Sorry. So the third one is the median. Okay. The third sample item will be 5. Okay, 5. Then what is the first quartile? The first quartile we calculate 0.25 times n plus 1. Again, n is 5 here. So we calculate that is 1.5. It's not integer. So that means we need to take the average of... where is it? We should take the average of the first and the third, the second. Okay, so the first plus the second divided by 2. Okay, and the first is 2 sample item. The second sample item is 3, right? It's here, right? Divided by 2. So that's the first quartile. For the third quartile, similarly, we calculate 0.75 n plus 1, so 5 plus 1. So it's 4.5. So that means we should take the average of the fourth and the fifth sample items. And the fourth is 6, right? And the fifth is 7. Okay, I just skip the details so you know how to calculate the quartile and median. It's not very complicated. Right? Okay. Here is another new definition called mode. Okay, so mode is measurement which occurs most frequently. Okay, for example, we have data sets 2, 4, 9, 8, 8, 5, 3. Okay, so here we have 8 occurs twice. Okay, so that means the mode is 8. In this set, we have 2, 2, 9, 8, 8. 5, 3. So both 2 and 8 occurs twice. So here we have 2 modes. Okay, we also call that bimodal. Okay, bi means 2, right? Okay. And here set is 2, 4, 9, 8, 5, 3. So we have no mode because each value is unique, doesn't repeat. Okay, so that's the idea of mode. Sample statistics and population parameters. Okay, so last time we talked about what is sample and what is population. For example, we want to know, the sample size, the diameter of the last 1,000 rod. So the engineer take a sample of 50. So in that case, the population is 1,000 and the sample is 50. Okay. Numerical summary of a sample is called a statistic. For example, the average diameter of that 50 rod, okay, that is a statistic. On the other hand, a numerical summary of a population is called a parameter. So the average value of that, the whole 1,000 rod is a parameter. Okay, so statistics are often used to estimate parameters. So we try to estimate what is the average value of the 1,000 rod based on the average diameter of the 50 rod. Okay. All right, again, here shows us what is the population. Population including all the items in that space we want to study. Sample is, for example, simple random sample. We take a certain sample item from the population and measure, for example, the mean value, standard deviation, and so on. Okay, and we try to get the idea of the parameters, the mean value of the whole population, the standard deviation of the whole population, based on that information from that sample. Okay. And basically, the equation to calculate parameter and statistics is the same. For example, the equation to calculate the population mean is almost the same as the equation to calculate the sample mean. Okay, all the equations are very similar. All right, and here is the population mean. Right. So if we can enumerate the whole population, then the population mean, we call that mu. Okay. Also, we can write as this. E is for expectation, is equal to the sum of xi times p, xi equal to xi. That means the probability for the sample item equal to xi. So that's the probability. Okay. If the probability for each sample item is the same, such as we do a lottery, okay, so then the mean value will be simplified as this. Okay, the sum of all the sample item together divided by the whole population number. Okay, so that's the equation we know of. For the variance of population of n measurement is the average of the square deviation of the measurement about their mean value mu. Okay, so the equation is very similar to S squared, which we discussed in last class. So S squared is the sample variance. Okay, sigma squared is the population variance. Okay, as we can see, the equation is very similar. Okay, the only difference between sigma square and S square is, so here for sigma square is divided by n, but for S square is divided by n minus 1. Remember last time we talked about why we need to divide it by n minus 1, not n. Okay, so again you can see the equation for mean and variance for the population and the sample are pretty much the same. Very small difference. All right. Next, let's look at so-called events.
Sorry, but what does the E stand for in the population mean?
P is the probability. So probability for that happen. Okay. So Pxi equal to xi means the probability. Yeah, that number happened. You mean P, right? E Oh, E is called expectation. Expectation is for E. Okay, is another word for mean value. It's not used very often. Most likely we use mu. Okay, mu for the population mean. Okay, but E is for expectation. All right. So event is outcome of an experiment. For example, we toss a die and we observe the number of that appears on the upper face. Okay. So here are some of the example of events. So event A, let's say, is defined as we observe a odd number. Okay, for that die, odd number means including we observe a 1, 3, and 5. Right? Okay. So event B, let's say, defined as observe a number less than 3. For that die, less than 3 include what, 1 and 2, right? 1 and 2. Right? And we can see both event A and event B occurs when the upper face shows a 1, because 1 is odd number and 1 is also less than 3. Okay, and event E1 defined as observe a 1, E2 get a 2, and so on. Okay, and that's all the possible outcomes for the experimental of tossing a die, right? So only outcome is we get a 1, 2, 3, 4, 5, or 6. No other possible outcomes. And two events are mutually exclusive. Sorry, if one event occurs, the other cannot, and vice versa. Okay. For example, E1 and E2 are two mutually exclusive events. For example, if we get a 1 on the upper face, we cannot get a 2 on the upper face, right? And same and vice versa. So these two events are mutually exclusive. And event A, which is we observe an odd number, can be further decomposed into simpler events. For example, event A can be decomposed into the upper face shows a 1, or shows 3, or shows 5. And event B, which is defined as we observe a number less than 3, can be further decomposed into E1 and E2. So we get a 1 or get a 2. Okay. An event that cannot be further decomposed is called a simple event. Okay. For example, E1. E1 is the upper face shows 1. So that's the simple event because it cannot be further decomposed into even simpler events. Okay. And the set of all mutually exclusive simple events is called a sample space. Okay. For example, for the experiment of tossing a die, the sample space including E1, E2, E3, E4, E5, and E6. So that's all the possible outcomes for that experiment, which is tossing a die. Okay, so that's called sample space. Okay. And an event is a collection of one or more simple events. Okay, so we learn what is events, what is simple events, and what is the sample space, and what is defined as mutually exclusive. All right. Next, let's look at summary statistics. Okay, for categorical data. Okay, the most commonly used numerical summaries for categorical data are frequencies and sample proportion. Okay, sample proportion has another name called relative frequencies. Okay, so let's look at what is frequency and how they define. So we can use the delta distribution to describe, first of all, what values of the variables has been measured. So what are the possible values and outcomes? We can also measure how often each value has occurs. Okay. And that how often can be measured in several ways. So first is called frequency. For example, if we observe 8 twice, then the frequency for 8 is 2. So frequency is equal to 2. So for example, if we observe a value totally 10 times and we observe 8 twice, then we can calculate relative frequency, which is equal to frequency divided by the total number of observation. Okay, for 8, it is 2. We observe 8 twice, divided by total number of observation 10. So 2 over 10 is called relative frequency. Okay, if that value times 100, that's the percent to observe a certain number, such as 8. Okay. So let's look at an example. Right? So here we have a bag of M&M candies. They have different colors. Total number of candy is 25. We have blue, red, yellow, green, and brown color. Okay, so we can do a table to summarize all these different candies depending on the colors. Okay, we have 6 different colors, and we can count the frequency. Again, frequency is how many times for a certain category occurs. So for red candy, we have 5. Okay, 1, 2, 3, 4, 5, and so on. We can do the count totally for all the different colors. So you can add this number all together to make sure it is equal to the 25 total candies. Then the relative frequency is the frequency divided by n, and here is 25. Okay, so relative frequency for red is 0.2, so the percent is 20%. So that means for a bag of 25 candies, 20% of them is red. Okay, and then based on this table, we can put them into graphs. So later in this class, in this lecture, we're going to learn how to plot different type of graphs. Okay, so this is a bar chart, and this is the pie chart. Okay, for bar chart, the x-axis is depending on the color, different colors, and the frequency is the y-axis. For example, red candy, it occurs 5 times, so that's 5. Okay, so very simple. We can put the percentile in a pie chart. Typically for a pie chart, it's 100% in total for the whole pie. For red is 20%. We can write here, red, the frequency is 5, the percentile is percent is 20%. Okay, so that's pie chart. So I think most of us has seen this type of charts before, right? Okay, so this is section 1.2. The next session, we're going to show how to draw different type of graphical summaries, okay, from stem and leaf dot plots, which are not used very often actually, to histogram, box plot, and scatter plot. Okay, among these, the histogram and the scatter plot are used very often. Okay. Let's look at the stem and leaf first. Okay. So it's a simple way to summarize the data set. Okay. Each item in the sample has 2 parts, a so-called stem and leaf. Okay. The stem consisting the leftmost 1 or 2 digits, and leaf consisting the next digit. Okay. And for stem and leaf plot, it can show all the data points. Okay. Can also show us the shape of the data. Okay. We're gonna have a look of example. All right, here shows this is the duration of dormant period of geyser called Old Faithful in minutes. Old Faithful geyser is the very famous geyser in Yellowstone National Park. I think many of us heard that before. Okay, and that table showing us duration of dormant period, which is the between two eruptions in minutes. Okay, and we put this data in the stem and leaf plot. Okay, for example, 42, the stem is 4, we put a 2 here. Okay, we also has a 45, so we put a 5 here, means under 40 we have 42, 45, and 49. Okay, for 50s we have 50, 50, 51, and we have 4 51s. As we can see from here, we have 253, 255, and so on. So use the stem and leaf plot, we can represent all the data points on that table 1.3. Here is another example. So we have a price of 18 grams of shoots. Okay, that's the price in dollars. Okay, first we put double digit into the stem. For example, and the 40 we have 40. Okay, and that's it. Under 50 we have nothing here. Under 60 we have 65, 68, 68, and another 68. Okay, and so on. Okay, but after we do that, we should reorder in this format. Okay, for example, under 60, we should arrange from small to large. Okay, 0 here, 5, 5, 5, and 8, 8. Okay, so you get the idea how to plot the stem and leaf plot. Okay, so very straightforward. And this type of plot is not used very often, but we should at least understand what it is. The next is called data plot. It's similar to the stem and leaf. Data plot is not used very often either. That's the graph. Can also be used to give a rough impression of the shape of the sample. Okay. It is used when the sample size is not huge, okay, and when the sample has some repeated values. Okay, and based on the dormant period of the Old Faithful geyser. Okay, so if we plot that in the dot plot, it will show something like this. For example, under 80s, we have 4 80s, and so on. So each dot represents one dormant period in minutes. Okay. And here's another example. So all the data point here, so we can put that in the dot plots. Okay, we have 3 5s, 1 4, 1 6, and 1 7. Okay, let's continue. Oh, and 2 6, sorry. All right, so this is another example. This is a quality control process. Measure again the diameter of the gear. Okay, so record 15 diameters, as we can show from here, but that's the typing mistake. Okay, so if we put that in the dot plot, we can show the typing mistake here. Okay, so we call this type of data, which is much larger or much smaller than the remaining of the data set, we call that outliers. Okay, so outliers could be caused by typing mistake, or outlier could actually be a real accurate data. Okay, So in this case, we can easily see an outlier in the plot. Okay, the third type of plot is called histogram. Histogram is used pretty often. Okay, so it can give idea of the shape of the sample. Okay, and sometimes we want reasonable number of observation in each intervals. Okay, the bar of the histogram should touch each other. Okay, if that's the case, if we have space, that means there's no observation in that interval. Okay, so we're gonna see an example quickly. All right, we can put histogram into a relative frequency, which means the height is the relative frequency. Okay. Okay. So first we create intervals based on the range of the data. Okay, and then the interval should be the same in most cases. And then we stack and draw the bars based on how many data points fall within each interval. Okay. Like this. And then we can draw the height. So the height could be relative frequency or the frequency itself. And here shows the detailed steps how to create a histogram. Okay. So first of all, we need to divide the range depending on the total range of the data from the smallest to the largest. Okay. The range should cover the smallest sample item and the largest sample items. Okay. So we divide into around 5 to 12 intervals with same length. Okay, and then we should calculate the width, okay, which is the range divided by number of intervals. Okay, and then we should round up the width to a simpler value. Okay, and we should use a so-called left inclusion. I'm gonna show that in a moment. What does that mean? And then create a statistical table including the subintervals and frequency, and then relative frequencies. Okay, and then we should draw a rectangular and based on the frequency or relative frequency. Okay, and that's all right. And the height of the bar could present the proportion of the measurement fall in that certain class or subinterval. Okay, and all the probability that a simple measurement fall into that class. Okay, so use an example to show us how to plot a histogram. It's pretty straightforward. Okay, all of the steps is complicated. So here shows the ages of 50 tenured professors at a certain university. Okay, so this is the raw data. The first step is we look at what is the smallest value, the youngest, 26, and what is the oldest, the 70. So that will determine the range. Okay, the range will cover 26 and 70, the smallest and the largest. Okay, so let's say we choose 6 intervals. Okay, you can choose 7 or 8, doesn't really matter. Okay, and then the minimum class width will be largest age, the oldest minus youngest divided by 6, 7.33. So we should choose the simpler value. Let's say we choose 8 for each class. Okay, so for 6 intervals, each 8, so 6 times 8, 48. So let's say we start at 25. Okay, so 25 is smaller than the youngest professor, so that's okay. should cover the range. And then we should do the tally. Okay. For the first interval is from 25 to less than 33. Okay. This is left inclusion means. If it's equal to 25, it is included in this class. Okay. If it's equal to 33, it belongs to the next class. Okay. So large or equal to 25, but smaller than 33. And then we do the tally. Here is frequency. Again, frequency is how many times the age of professor fall into that age class. Okay. And relative frequency is frequency divided by total number of professors. So 0.1 and percent is 10%. And then we are ready to plot the histogram. Okay, so we can use relative frequency as the y-axis, the height of the histogram. Okay, so the first class 25 to 33, next is 33 to 41. Okay, so we can do that. And height is relative frequency. All right. So based on this histogram, we can draw some conclusion. Okay. First of all, what is the shape of histogram? It is skewed to the right, which means the right side has the longer tail. The left side has shorter tail, so we call that skew to the right. And the outliers, outlier again means value much larger or much smaller than the remaining of the sample items. In this example, there's no outliers. Okay, and we can also answer some of the questions. What proportion of the tenure professors are younger than 41? Okay, so younger than 41, if we just add frequency here in this class plus this is 14 plus 5, so 38% of faculty are younger than 41. Okay, and also what is probability and randomly select faculty member is 49 or older. Okay, 49 is here, so 49 or older means belong to the next left 3 bars. Okay, so that's 9 plus 7 plus 2 divided by 50. So 36% a randomly select faculty member is 49 years old or older. Okay. Here is another example of histogram. This is the emission, I believe, for certain type of vehicles. Okay, gram per gallon of gasoline. Okay, and here shows the relative frequency. Okay. Here is the histogram for the dormant period for the old faithful gasser data. Okay, and we can see here we have basically two peaks. Okay? One peaks here, another peaks here. Yeah, histogram is used very often in all disciplines. Here's another example. I think it belongs to traffic engineers. Show at different months. Okay, again, this is the emission data. Okay, and also for the depending on different road conditions. So we can plot histogram into a 3D samples, which means he has 3 variables. Okay, so here's another one. Oh, this is the upper limit of load range for this Excel. For this is time in months, and this is the emission, I believe. Okay, All right, this is another histogram. This is the final grades of exam. Okay, so for different grade range, this is the frequency, which is number of students in that range. And we can see here is the mode, the highest, and we have longer tail on the left, and we call this skewed to the left. Okay. All right.
I have a question.
Sure.
I was just wondering, it says, how do you choose how many intervals you want for the histogram?
You have the freedom basically. As long as it's
Oh,
normal,
okay.
you set from 5 to 12. You can pick up whatever number you want. Okay. Just the interval
Okay.
should be some simple values, not like a 6.7, but something like
Right.
8, 10. Okay. Yeah, doesn't really
All right,
matter.
thank you.
Yeah.
Oh, okay.
Yeah, but the interval, the weights of each class should be the same.
Right.
Yeah.
Okay, thank you.
Okay. You're welcome. Good questions. And the histogram is called perfectly symmetric if the right half is the mirror image of the left half. Okay. And if that's not the case, we call that skewed. If it has a longer right-hand tail, it is said skewed to the right. It's also called positively skewed. Okay, so here give example, income right skewed. Okay, so guess we have some billionaires. So the right-hand tail is much longer. Okay, but the frequency is much smaller. And skewed with a longer left-hand tail is called skewed to the left or negatively skewed. Okay, for example, grade on the easy test are left skewed. Okay. All right, and last time we talked about mean and the median. So these two parameters are very similar. Okay, if the histogram are symmetrical, then the mean value and the median will be very close to each other. Okay, if the histogram is right skewed, has a longer right hand tail, then the mean value will be larger than the median. Okay, if histogram is left skewed, then the mean value will be less than the median. Okay, again, the mean value is defined as the average of the sample items. You add all the sample item value together and divide by sample size. The median is the 50th percentile, the value in the middle. Okay. A histogram with only one peak is called unimodal. Okay. With two peaks are called bimodal model, and more than two peaks are multimodal model. Okay. So that is the histogram. All right. Next, let's look at box plots. Okay. I will say box plot is also pretty much useful. Okay. It shows us the quartile and also where is the median as well as the outliers. Okay. A box plot is graphic that represent the median, first, third quartile, and outliers. Okay. There's also a so-called interquartile range, which means the range between the first and third quartile. Okay. And here shows the steps how to draw a box plot. So we need to calculate what is the median, what is first and third quartile. Okay. And then we need to draw a lines based on that. Okay. Then we should find the largest sample, which is less than 1.5 IQI. IQI is quartile range. between the first and third quartile, and also the smallest sample values less than 1.5 IQI. Okay. And then we should just draw some vertical lines, we call that whiskers. Okay, don't worry, we're gonna show you an example. All right. Then the point more than 1.5 IQI above the third quartile, or more than 1.5 IQI below the first quartile, they are called outliers, and we should plot outliers individually. Okay. So this is the typical box plot. So this line is third quartile, this line is the median, this is first quartile. Okay. And also we should draw the smallest data point within the 1.5 IQI, then a line between here and here, we call that whiskers. And similarly, we draw another line connecting the largest data points within the 1.5 IQI and the third quartile. Okay, and then we should plot all the outliers individually. Okay, so this box plot showing us the old faithful Gezer, the Dolman period. Okay, and we can see some notice from here. First of all, there's no outliers because you're gonna plot any outliers individually, no data points, so there's no outlier here. We can also see the sample values are densely packed between the median and the third quartile. So here, this line is the third quartile, and this line is the median. Remember, the data points between these two lines take 25%, okay, because this range is smaller than the other range, so we call that densely packed between the median and the third quartile. Okay. We can also see the lower whiskers here a bit longer than the upper whisker, this line. Okay, that shows the data is slightly longer lower tail compared to the upper tail. Okay, it's skewed to the left. Okay. And also some other information. The distance between the first quartile and the median is greater than the distance between the median and the third quartile. Okay, so here is the median and here is the first quartile. Okay. Right, so after you plot the box plot, we can also compare them side by side. Okay, so we can compare what's the median, the difference between the median and also the first and third quartiles. Okay, and also the difference between the spread of two samples. Okay, so here is how we draw a box plot. First step, Q1 first quartile, the median, and Q3 the third quartile, and also the interquartile range, the IQR. Okay. Then we draw a horizontal line represent the scale of the measurement. Okay, this is QI, this is the median, this is Q3. And then we draw a box based on the Q1, the median, and the Q3, like this. And then we should draw the outlier and the whiskers. Okay, so first we need to isolate the outlier by calculate the lower fence. Okay, so the outlier is defined as the values smaller than the lower fence, which is Q1 minus 1.5 IQI. All the values larger than the upper fence, which is Q3 plus 1.5 IQI. So this is the fence, the green dotted line. So this line is the lower fence, and this line is the upper fence. Okay, so outliers is outside this range. Right, and we should again plot the outliers individually. And whiskers should connect in the largest and the smallest measurement that are not outlier, which means the smallest value which is not qualified as not outlier, and also the largest value which is again not qualified as outlier. Okay, and we connecting that points with QI and Q3, so that's called whiskers. So box plot is pretty useful. Okay, the last one is called scatter plot. Okay, scatter plot is, I will say, by far the most important plot. Okay, we discussed today. I use that very often. So we do research on concrete materials, and we always plot scatter plot because we try to find correlation between certain parameters. For example, how the strength of the concrete is affected by certain value, such as the temperature or water to cement ratio. So we try to find a correlation between the strength and these parameters using scatter plot. Okay, so data from which item consisting a pair of value is called bivariant. So for each sample item, we measure two values. Okay, and we have two scales, XXL and YXL. Okay, and based on that, we can see if there's a trend or correlation between X and Y. Okay. So if the dots on scatter plot, are spread out in a random scatter, then probably these two variables are not well related to each other. Okay. If the dots are spread around the straight line, that's very good. Okay, or not even a straight line, or some other type of line, then probably there's a correlation between these two parameters. Okay, and we should further look at these two parameters. Okay. And if we can find that correlation, then variables may be used to help predict the value of other variables. For example, if we can find the correlation between temperature and the strength of the concrete specimen, then we probably can predict the strength based on its temperature. Just give you an example. Okay. All right. Okay. So we finished all the important parts for chapter 1 in first week. We discussed different type of data, okay, and also look at how to do the sampling. Okay, the reason we do sampling is we try to draw some information or conclusion of the whole population from a small sample. If we can, we should use SRS or simple random sample. If not, we can use sample of convenience, and then we should think carefully if that will be representative of the whole population. Okay, and we also learn about the sample statistics. What is the mean value? What is the median? Percentile, quartile, and so on. Okay, and also we learn how to plot different type of graphical display of data, including histogram, scatter plot, and so on. Okay. So yeah, that's the end for today's lecture. So we finished